Sure, yeah.
Right. Okay, so now we're going to get into Shor's algorithm. And there's certain background things you have to know in order to know why Shor's algorithm. So a non-trivial square root of 1 is a number y such that y squared equals 1 mod n. So a non-trivial square root of 1 mod n is some number such that y squared equals 1 mod n, where y is not 1 or minus 1. If y were 1 or minus 1, it would be a trivial square root, but a non-trivial square root is where it isn't. So an example of that is mod 15, 4 times 4, 4 squared is 1 mod 15. Now, if you happen to know a non-trivial square root of 1 mod n, you can factor n, and I'll explain why that's the case. And RSA is a periodic function. What I mean by that is if you take some number a, raise it to the power 1 mod n, then raise a to the power 2 mod n, and just keep doing it, eventually it will loop and get to the same numbers again. So that means it's kind of periodic, that you'll get the same answer spaced a certain amount. And if you know the period, you know when it repeats, and let's call that d, I'm defining d to be how many numbers you go through before it repeats. And if you know d, you'll be able to find a non-trivial square root of 1 mod n. And if you can do that, then you can factor n, which means you can compute private keys from public keys. So what does it mean that it's a periodic function? So if you compute a to the x mod n, starting at 0, eventually you'll get to, you'll find a number d such that a to the d mod n equals 1. And if a to the d mod n is 1, that means for any exponent x, a to the x mod n is the same as a to the x plus d mod n, because multiplied by 1 you get the same thing, is equal to a to the x plus 2d mod n, etc. So this is what Shor's algorithm is going to help us do. It will help us find the period d, and as I said, that will help us factor it. So why can you factor n if you know a non-trivial square root of 1 mod n? So let's say that you know that y is a non-trivial square root of 1 mod n. That means that if you know that y squared mod n is 1, because y is a square root of 1. So that means that y squared minus 1 mod n equals 0. You just, this is like, I don't know, 11th grade math or something. And then you can factor that. Y squared minus 1 is y plus 1 times y minus 1, and that equals 0 mod n. And the only way, or alternatively, y plus 1 times y minus 1 is some multiple of n, which is the same thing as being 0 mod n. And how can that be, that y plus 1 times y minus 1 equals 0 mod n? It can either be where y plus 1 or y minus 1 is 0, in which case it's a trivial square root because it's either 1 or minus 1, or y plus 1 and y minus 1 are factors of some multiple of n, which there are only, in an RSA modulus, it's the product of 2 primes, p and q. So it'll be that one of them is p and one of them is q. So if you compute the greatest common divisor of this non-trivial square root of 1 mod n, with n, you will find out either p or q, and then you've now factored n. So let's say that you know this period d. Why does that help you find a non-trivial square root of n? So if you know that the period of a to the x mod n is d, then what you can do is you know that a to the d mod n is 1. So now you know that a to the d over 2 mod n will be a square root of 1. So suppose a to the d over 2 mod n is 1. Well, then it's a trivial square root, but that means that a to the d over 4 mod n is also a square root of 1. So you can start at d and keep dividing d by half, and you will either get to a non-trivial square root of 1, or you'll get to minus 1. Now, you don't want to get to minus 1, because then you're kind of stuck. If you get to minus 1, then you have to choose a different a and start over again. But about half of the a's will result in your getting a non-trivial square root. And as I said, once you know non-trivial square root, you're golden. So the Shor's algorithm is going to allow us to compute d. And from there, it's going to be really easy to factor. Okay. So, yeah, about half of the a's, you'll succeed at this. So it's not going to take you very long once you know the period. So if we raise a to the x mod n from 1 on up, the number repeats every d. And we'd like to find d so we can factor n. And that's what Shor's algorithm is going to do. It's going to help us find d. So let's do Shor's algorithm. So let's say you want to break 2,000-bit RSA. So what you're going to do is you're going to use twice as many qubits as the modulus. So if the modulus is 2,000 bits, you're going to use 4,000 qubits for what I call the exponent qubits. And we're going to represent all values of x for a to the x, simultaneously. That's kind of what quantum computers do. So we're going to store that into the exponent qubits, and we need an extra 2,000 qubits to record the answer to a to the x mod n, and we're going to call those the answer qubits. So what we're going to do is we're going to take these 6,000 qubits, we're going to initialize them all to 0, and we're going to take the 4,000 exponent qubits and apply Hadamard's to all of them. So now, so the exponent qubits have superposed all 2 to the 4,000 possible values of the exponent. So what we have now is 4,000 exponent qubits that have equal probability of all the 2 to the 4,000 values, and the answer qubits are all 0. So the next step is with a quantum circuit, because that we want to do simultaneously on all the values, we're going to calculate a to the x mod n and exclusive OR the answer into the answer qubits. So now we have 6,000 entangled qubits where the exponent qubits have all possible values and the answer qubits have a to the x mod n for each value of x. So now, if you were to read the 6,000 qubits at this point, what you would get is some totally random value v in the exponent qubits and a to the v mod n in the answer qubits. This is not very useful. You could have done this by picking a random number, raising a to that, whatever, you'd get the same information that you get here. So we're not going to do that because that would not be useful. So instead, what we're going to do, this is just the most adorable thing ever, except for my kids, but yeah. So instead, we're not going to read the exponent qubits, we're only going to read the answer qubits. So you don't care what value you get, you're going to get some random number, q. But what are we going to do with that? So the entangled, once you read the answer qubits, all of the values, so you get q, all of the values of the exponent qubits for which a to the x mod n is not q, all of those go away. And you're left.
All of those are left. Everything else goes away.
is not equal to q. Those go away. And the only x's that remain are x's such that a to the x mod n equals q. So yeah, the exponent qubits, the only superposed values are values of x such that a to the x equals q, because you read some value q in the answer qubits. Okay, so if you were to graph the amplitude of each value of x, starting with a to the 1, a to the 2, a to the 3, and look at how much of that value of x is in the superposed quantum state in the exponent qubits, you will find that almost all of them are 0, except for values which of x for which a to the x equals q. And these amplitude spikes will be d apart. So this is great. This looks like really good. But the location of the first spike sort of depends on q, what value you happen to have read. So at this point, what you really want to do is you want to find the distance between these. But by reading them at this point, that's not going to be helpful. If only you could clone these qubits. If you could clone them and read it twice, you'd get 2 different values and they'd be some multiple of d apart. But you can't do that. So yeah, my son, who's a co-author on the book, is an expert on this, and I was grumbling to him. I don't like these rules. These are really annoying rules. And he said, don't blame me, blame God. But anyway, so what can we do at this point? It looks so promising if you look at the graph of this, but how can you get the actual answer back? So I'm going to call the graph that we just looked at the time graph. Those that remember Fourier transforms, we're going to do a Fourier transform. Those who don't remember what Fourier transforms are, forget that I'm using the term. So I'm calling this the time graph, just arbitrarily. And there's this thing called, and we're going to convert it to a frequency graph. So the number of values in the time graph is 2 to the 4,000, a number of, and Shor was inspired by Fourier transforms. He noted that there was a way to convert the time graph into what we're going to call the frequency graph, which is kind of the inverse of the time graph. So the frequency graph will have a spike every n, which is 2 to the 4,000, over d. So this number you want will be in the denominator in the frequency graph, which is, annoying because it was right there in the time graph, but no way to read it in any way. So the frequency graph will have spikes every n over d, but it will start with the first spike at 0. So you're guaranteed to read a useful number. It will be some multiple of something with d in the denominator. So, so after you do the quantum Fourier transform, which I'll explain what that is, you'll have spikes at every multiple of n over d. And it turns out, just to be truth in advertising, the spikes are a little bit messy because d will not exactly divide n, so it'll be spread over a few bits. This is actually what the graph might look like, but it doesn't matter. You'll get a number that's close enough to a multiple of n over d that you'll be able to figure out d. So how do you do this thing? Well, vectors, if you add vectors, if you have 2 vectors pointing in opposite directions and they're the same size, they'll cancel each other out. If you have 2 vectors pointing in the same direction, they'll reinforce. And if you have like a whole bunch of vectors that are sort of equally spaced pointing, they'll also cancel each other out. So how are we going to convert from the time graph to the frequency graph? So remember, this is what the time graph looks like. If you start with, every value of x, a to the 1, a to the 2, only some of those x's will have a positive spike there. So just kind of imagine that graph where every d, there's a spike. So what in the frequency graph, what the x-axis says is when the value 1, imagine this thing here on the bottom as a giant rubber band that has kind of, spikes coming out. And in the frequency graph, the x-axis, 1 means you take this giant rubber band and wrap it around a unit circle 1 time. If for the value 2, it means you wrap it around twice. Value 3, you wrap it around 3 times. So if you wrap around for the value f equals 1, you're going to wrap it around once. All these spikes will be pointing in different directions. So they're all going to cancel each other out. So in the frequency graph, you'll get a 0. But there'll be some value of wrapping around where the spike happens kind of at the same place each time. And at those places, it'll reinforce and you'll get a spike in the frequency thing. And if it's near that, like if you overshoot by a little bit, you'll have a bunch of spikes kind of pointing in the same direction. But, and that's just because of the messiness, because it doesn't divide equally. And so you'll wind up with a graph that looks like this. And if you read a spike, you'll get a value, which is very frustrating because d is in the denominator. It's not, the thing you want. But you have to do some calculations which are normal, efficient calculations on a normal computer called continued fractions. And that will enable you to get the denominator d. And so how many physical qubits would it take for to build a quantum computer that would do Shor's algorithm on 2048-bit RSA? Well, nobody knows exactly because, it depends on a bunch of things. But there's a paper that sort of is the best estimate right now. And it estimates that it would take 20 million physical qubits to break 2048-bit RSA. It looked like from my description, it's, hey, it takes only 6,000 qubits, but to do this whole circuit and whatever. Okay, so now I'll let Charlie talk for a while. By the way, did anyone sort of feel like they now kind of understand Shor's algorithm? Okay, well, it's a good introduction to it, and then at least you feel maybe that you could understand it, and then you could read it again, and each time maybe, okay.
Okay, so the next thing we're going to talk about, and this is a short subject here, is quantum cryptography. And it's interesting because it's actually a system that has been built and deployed, and it's actually practical in the sense that you can physically build it and make it work. Whether it actually has any useful value that you couldn't do better someplace else, some other way is subject to interpretation. So, what is quantum? It's also been called quantum encryption or quantum key distribution, and so there's assume this problem is that Alice and Bob want to agree on a secret, and they're at opposite, and they're far away and can only and they can send light beams to each other, but they can't. But they're worried that somebody in the middle might be able to see it. So what we're going to use is that it turns out that the polarization of a photon can be thought of as a quantum state, and so if you have a light beam and you polarize it. If you polarize it, up, down, you can think of that as being a 1-bit, and if you polarize it right, left, you can think of that as being a 0-bit. And then if you have any angle that's between there, that's sort of a superposition of 0 and 1. It could be anywhere in between. So the way you measure a photon is you put a polarizing filter, And if your filter is aligned with the polarization of the photon, then 100% of the time the photon will pass through, and you can then measure that it did that. If the polarization filter is 90 degrees off, then 100% of the time the photon will not pass through, it'll be absorbed. And if it's at an angle, then with some probability the photon will pass through, and with some probability it won't. And then the quantum magic is that once it's passed through that filter, it'll now be aligned with the filter, because that's a measurement, and once you measure it, it takes on the value that you measured. So we can actually observe this in real life, and sometimes we actually bring some polarization filters and do the demo. If you have two filters and set them 90 degrees off from each other, no light passes through, because any light that passes through the first filter is polarized with the first filter, and then it's completely absorbed by the second filter and nothing goes through. But if you take three filters and you put another filter between those two filters that were absorbing everything that's off by 45 degrees, now, in fact, 1/8 of the light gets through, because half make it through the first filter, half make it through the second filter that was 45 degrees off, and not only did it filter things and absorb half of them, but it also shifted the other ones 45 degrees, which now caused another half of those to make it through the third filter. And so it's quite a mysterious effect. You see these two things that no light can pass through, and then you pass a filter in between them, and all of a sudden now some light's going through. Right, so quantum cryptography, we're going to, how do we send random bits from Alice to Bob? Well, they have to be able to do some sort of integrity check, because they need to be able to send messages to each other that anybody might be able to read, but they need to know that they're really talking to each other for purposes of that message. And we're going to have a single hop fiber optic link that we're going to be sending individual polarized photons down for them to communicate. So it's a quite tour de force that people can actually build this thing, but they have, and they've demonstrated them, and it actually works. And in addition to working over a fiber optic link, it's also been demonstrated to work over great distances on laser beams between satellites. And so they've shown large numbers of kilometers of things and it can actually go greater distances in space that way than it can in the fiber optic cable. So Alice is going to create these polarized photons. So Alice is going to send single polarized photon, and it's going to be polarized in one of four directions. It's either going to be vertical or horizontal or diagonal this way or diagonal this way, chosen at random one of the four ways. Then Bob is going to be listening, and he's going to have a filter that's also adjusted randomly in the positions, and he's going to note in each interval whether he received a photon or not. And so if he reads the photon when he has the when he has the up-down filter in place, if the photon was sent in an up-down, then 100% of the time it'll make it through. If it was sent horizontally, 100% of the time it won't make it through, and if it was sent in one of those other two positions, half the time it'll make it through. So, okay, so, and likewise with the diagonal filter, the same rules apply. So what happens is Alice is going to send down a series of photons, and Bob's going to have his filter set randomly and measure it. And then Bob's going to tell Alice, after this is done, and Bob noticed in each interval whether he received the photon or not, he's going to tell Alice what sequence his polarizers were set in. So first I set it this way, and then this way, and then this way. Alice is going to, if Bob chose a diagonal one when Alice chose a vertical one, then it might have made through, it might have made through, and we have no information, so Alice is gonna say, ignore the things that arrived in that time interval. But for the ones where our polarizing filters were set in a compatible way, we're going to use that as information to decide to set the bits of a key that we're gonna set up. So this way Alice and Bob can agree on this sequence of bits that they're going to use as a cryptographic key later on. Right, so of the remaining bits, Bob will line things up and do that. Now, if an eavesdropper was on the, broke into the fiber optic cable and was trying to watch what was going on, he could do the same thing that Bob is doing, but he's not going to know how Bob was setting his polarizing filters, and so so some of the times he's going to have set it wrong. And he can't regenerate, once he's read the thing, he can't regenerate it the way Alice sent it. And so what's going to happen is if there's an eavesdropper, then there'll be errors on the line because he'll retransmit things and Bob won't receive quite right. And so when Alice and Bob try to figure out what key they've agreed on, they'll get different keys and they'll discover that they can't talk to each other. Now, there will be some errors due to just the fact that the photons are cranky and there's noise and bad things happen. But others are, but if there's an eavesdropper, there'll be more errors. And so Alice and Bob need to send an integrity check, both to protect the information that was doing there, and then they need to use error correcting codes to recover the message if there was a small number of errors. But if there was an eavesdropper, then there will be a large number of errors. And so if there's a more than an expected number, then they have to suspect that there's an eavesdropper on the line. And otherwise, they now know that they've conveyed this message with integrity. They now have a key that they can use to encrypt the data that goes by. And so,
skip this one. Why it's called quantum encryption. Let's skip that.
Okay. So why is this useful? You can't do this unless you already share a secret that you're using to do these integrity checks. And so if you already share a secret, you could just do conventional encryption. So why does anybody want to do this? Well, quantum key distribution can protect you if that shared key is later compromised. So if you have a key that you can use to protect the integrity of it, you can now generate this key that even if the long-term key is later compromised, nobody can eavesdrop on the conversations that you've been having in the meantime. This is exactly the same kind of guarantee that Diffie-Hellman ephemeral key agreement will provide for you. But people are saying, well, Diffie-Hellman with ephemeral key agreement could be broken by a quantum computer. And this can't, because this is based on quantum mechanics, and so you can't break it. And so that's an argument for using that. But you could also do it based on one of these quantum safe algorithms that's coming out. So
we want to get to the good stuff.
Right. So basically, the bottom line is that it only protects you in some fairly far-fetched scenarios, but because it's actually practical to build it and you can make it work, there are companies that have commercial products that do this, and there are some banks that are paying enormous amounts of money to get their fiber optic links protected in this manner. In my opinion, they're probably wasting their money, but but they get bragging rights for using this cutting-edge technology, and it is protected in case somebody's built a quantum computer that nobody knows about yet.
So, yeah, right. It gets a lot of press. It has nothing to do with, like if someone says, well, I can send like 1 billion bits per second using this thing. It has nothing to do with progress towards making an actual quantum computer. They're just, the same word in there. So, okay, so we're going to now talk about post-quantum algorithms. Other names for it are quantum resistant, and they're actual normal algorithms that run on classical computers. They just don't depend on it being difficult to factor numbers. They are not things that Shor's algorithm would be able to break. And they're based on other math problems that we hope that nobody will invent some sort of quantum algorithm to break them, or that somebody more likely would find a classical way of breaking it. So, as I said, if there were quantum computers, our currently deployed public key algorithms would be broken by Shor's algorithm. So most post-quantum algorithms either only do signatures or only do encryption. And why would that be? RSA can do both. You know, you use your public key to encrypt and your private key to decrypt, and you use the private key to sign. But RSA is kind of special because for any number X, applying the public key to X gives you a unique answer, and applying the private key to X gives you a unique answer if you ignore padding, which makes it so that you would recognize that this was not a real thing encrypted the right way or something. There's also this distinction that's really boring, but if you are going to be reading some of the specs, you'll hear about key encapsulation mechanisms versus encryption. And I think they used to think it was going to be an interesting distinction, but you can just ignore that. And it's the same thing, a key encapsulation mechanism or an encryption thing. It's a way for Alice to send Bob, for them to agree on a secret. So how do you make a scheme? Well, you find some math problem that you hope is hard because mathematicians have been trying to come up with good solutions and they don't. And then you have to somehow turn it into a cryptographic scheme. And the current proposed schemes are based on, you know, these words that will become less mysterious in a minute, you know, lattices and error correcting codes and stuff. So we'll talk about whatever we have time to talk about, but they're all interesting in their own way. So NIST, standardized AES, and SHA, a hash algorithm, an encryption algorithm. And the way they do this is there's this group, which my son is in, which is really cool. So they solicit proposals for these things, and then they don't want to propose algorithms themselves, because if they're kind of choosing them, that would not be good. But anyone from all over the world can propose algorithms. And the NIST has been pretty much accepted by the world as being unbiased and competent. And so NIST analyzes these things, but also the entire cryptographic community analyzes them. And then they have conferences with, you know, papers and stuff where these highly motivated cryptographers who want theirs chosen try to poke holes in the other ones. And after a while, they choose one or several schemes and they standardize them. So the way the thing is, they say, well, we want to have a scheme. If you want to do a proposal, it has to be a scheme that with different parameters, it can achieve one of, you know, they have 5, but let's just look at 3 security levels. One is equivalent to 128-bit secret key, or 192-bit secret key, or 256-bit encryption keys. So the schemes are hard to read, and they're like full of parameters. There are parameters for each security level, and there are also parameters for making trade-offs, where you might decide to make a time-space trade-off or something so you can, you know, do the algorithm in different ways. Now, some quirks of some of the schemes, which, you know, is like bizarre. I might have a scheme where I can encrypt something for you, but the scheme might have a decryption failure where I send it to you and you can't decrypt it at all. Or you decrypt it to a different answer than the one I had encrypted. You know, this doesn't happen with RSA, but it can happen with these things. So you try to design your scheme with parameters and stuff to make it very unlikely that you'll have a decryption failure. Oh, right, and a decryption ambiguity where I encrypt the number X and you decrypt it and get the number Y. So, and as my son keeps saying, it's not a competition, it's something else. And the reason for that is there were some sort of rules about it. If it's a competition, it has to whatever. So NIST tries to say, no, it's not. it's a process, it's not a competition, whatever that means. So the original deadline was December 1st, 2017. They received about 80 proposals. My son broke 5 of them the first week, and they've kind of whittled it down. And so we'll give intuition into some schemes. So some general concepts of finite fields. So this is like modular arithmetic. So modular arithmetic, we talked about, that enables you to know the size to represent an integer. But suppose your modulus is not exactly 2 to the n. You know, let's say your modulus is 23. Well, that would require 4 bits, right, to represent it, and that's kind of wasteful. No, 5 bits. 5 bits, because if it's only mod 23, there's these extra values between 24 and 31 that you can't represent. So there's other things called, finite fields where the size of the integers are a power of 2, and therefore it will exactly fit in there. And the math for it is a little bit more complicated to understand, but it's super efficient on computers because it involves things like XORs, which computers love doing. Okay. Another thing that's kind of relevant in these schemes tend to involve matrices. So large matrices where they have hundreds or thousands of dimensions. So if you have, if each element in the matrix requires b bits to represent, and a matrix is 500 by 500, then to represent that matrix would take b times 250,000 bits to represent. So these would get like really ugly, but there's this amazing optimization where you can specify just the top line of the matrix, and then you can derive the whole rest of the matrix from that. And so there's a kind of matrix known as a circulant matrix, where all you have to do is specify the top row. The second row is the same as the top row, but everything's shifted off by 1, and whichever gets kicked off comes in the other side. And so this is an example of a circulant matrix. So you'll notice that everything is being shifted right. One thing, and whatever fell off the other side gets brought in on the left side. And so to tell you this matrix, all I have to do is tell you the top row, and you know what the whole matrix is. And what we're doing here mathematically is if you think of the top row as a polynomial where each of the elements in the row is a coefficient of one of the elements of the polynomial. So if the row is A0, A1, A2, A3, the polynomial is A0 plus A1 times X plus A2 times X squared, and so forth. And so to get the next row is you're multiplying the previous row by x and reducing by x to the n minus 1, and this is sort of justifies your doing that. So the cool properties of doing it this way, if you have 2 circulant matrices and you add them, you get another circulant matrix, and the product of 2 circulant matrices is again a circulant matrix. So all you have to do is multiply the top rows together, and you'll get another circulant matrix. So it makes things very, very efficient. The identity matrix, the thing that if you multiply something by that, you get the same thing, that's also a circulant matrix. Anyway. And if you have the inverse of a circulant matrix, will also be a circulant matrix. So even though you're, in theory, doing all this stuff with matrices, you really can just do it with polynomials. So, this is a very, very important optimization of these schemes. So let's do lattice-based cryptography. So what's a lattice? Well, a lattice is a set of points that's generated from what's called a set of basis vectors. So any linear combination of the basis vectors is another point in the lattice. So here's an example of a lattice where the basis vectors are 0, 3, and 1, 0, and it will generate all of those points. Now, you could generate exactly the same set of points with lots of different bases. So the same set of points, so if you have the basis vectors 0, 3, and 1, 0, you'll get those points, but you'll get exactly the same points if you have 5, 6, 12, 15, those two basis vectors. So the same set of points can be generated with what the mathematicians call a good basis, which is one where the basis vectors are small, or with a bad basis where the vectors are large. So here's an assumed to be hard lattice problem, which is that if I give you n coordinates, a random point in n-dimensional space, which is just, I give you n numbers, find a nearby lattice point. So that's assumed to be hard if you don't know a good basis. If you only know a bad basis with the big basis vectors, you can't find a nearby lattice point. But if you know a good basis, you can find a nearby lattice point. So just believe that that is something you can do with a good basis and can't with a bad basis. So how do you make a public key encryption scheme with this? Well, Alice can generate a lattice, can define a lattice by choosing a bunch of basis vectors that are small. And just imagine, sort of picking small numbers, and she manages to get a basis. That is her lattice. She can turn that into a bad basis by taking her good basis vectors and multiplying them and adding them in various ways. So to get an equivalent basis for the same lattice, but with a bad basis, with long numbers. So Alice's public key will be a bad basis for her lattice, and her private key will be a good basis for her lattice. People okay here? Okay, so right, you can imagine Alice creating the large basis by just doing some linear combination of the small ones to come up with big ones. So how can Bob send a secret value to Alice? So Bob knows a bad basis for her lattice. So he can use the bad basis to come up with a point in Alice's lattice by just taking the bad basis vectors and do some linear combination of them, and he will wind up with a point in Alice's lattice. But then he chooses like a little offset from there. So he picks what's called an error vector, which is a small vector, with just small numbers, adds that to the random lattice point that he calculated using the bad basis. And so if L is the lattice point, what he does is he adds this little thing, the error vector, to it, and he gets some point that's not in the lattice. It's just sort of a random looking point in n-dimensional space. And that's what he tells Alice. He tells her that point. And because Alice has the good basis, she can find the nearest lattice point, L. And then she can subtract L from P to get the error vector. And it's the error vector which is the secret that Bob is sending to Alice. Okay? Right, so the hash of this error vector is the secret that they're going to share. So, okay, so let's see, how are we doing on time? Do you think it would be better to talk about some other scheme or to demystify how she finds this?
I think it'd probably be better to
go on to another scheme. Yeah, okay, so that sort of should demystify what lattice-based encryption means. Bob uses her public key in order to pass a secret value to Alice, and because Alice has the good basis, she can actually find the thing that he sent. Okay.
And you should mention that it's only because there are hundreds of dimensions that it's hard.
Oh, right, yeah, with 2 dimensions, it's not hard, but these are going to have hundreds of dimensions, which makes it hard. Now, interestingly, people also tried to design how to use lattices for signatures. And so, yeah, it seems easy enough. So again, your public key is a bad basis, your private key is a good basis. And what you do if you want to sign a message M, you do a hash of M, which will be some sort of point. You just make it have, chop it up into n pieces, and it will be a point in n-dimensional space. And you prove that you know the good basis by finding the nearest lattice point. And this was proposed by extremely reputable cryptographers, some of the most famous ones. But it isn't secure. So, the reason it wasn't secure is that if you see enough signatures, you can kind of map how far the signatures are from random points, and with only a few hundred signatures, you can actually start finding some short basis vectors. So they did manage to fix the scheme, so they do have lattice-based signature schemes, which is that you don't find the nearest lattice point, you find a lattice point that's close, and they won't let you do that. So let's see. Let's go on to code-based, right? Because I really think, I'm supposed to end at 2:30?
Yeah.
2:30?
Yep.
Oh, okay, so we,
Half an hour.
oh, okay, well, we could possibly do multivariate.
I think we could do multivariate.
You think we should do multivariate? Okay. Okay. So a multivariate scheme is based on it being difficult to solve a bunch of nonlinear equations. Linear is where you have x's and y's and you never multiply x's and y's together. Quadratic would mean that you can have terms which are x or x squared or y or xy, that kind of thing. And those are very difficult to solve. Nobody really knows how to do it more efficiently than just plugging numbers in and seeing if you can find something that satisfies all of the equations. So reviewing linear equations, this is something you learned in, I don't know, I keep picking 11th grade. It's
Might be 10.
10th grade, okay. So in a linear equation, each term in it only has a single variable. So like 3x plus 2y plus 46z equals 79. That's a linear equation. And if you have like 3 equations with 3 unknowns, you can solve it. And the way that you solve it is you take one of the variables, in this case, I guess y, and you take one of the equations and use it to express y in terms of the other ones, plug that alternative representation of y into the other equations, and now you have n-1 equations and n-1 unknowns until you eventually, so that's how you solve these things. So, right, But a quadratic polynomial is one where each term has at most two variables multiplied together, or one squared. So 7x, these are quadratic polynomials, 7xy plus 11x squared, etc. That would be a quadratic polynomial, and no one knows how to solve those efficiently. So a polynomial becomes an equation if we set it to some value. So systems of equations. So what degree is it? So if it's a quadratic, it would be degree 2. How many equations there are and how many variables there are. Solving it means finding values of all of the variables that make all the equations true. So if you have 50 variables and 50 equations where the equations are degree at least 2, solving it is computationally infeasible. So, and again, arithmetic is going to be done over some small finite field. So let's make a public key scheme out of a multivariate system. So the public key will be a set of coefficients for a set of quadratic polynomials. The private key will be some magic trapdoor that allows you to solve this particular set of polynomials and equations. So an example multivariate signature scheme, this is actual scheme which, much to NIST's dismay, they didn't actually submit. And so NIST has been kind of beating them up to say, please submit it. We're giving you an on-ramp here. And I don't know if they've submitted or not. I hope they have. If you have 50 polynomials and 150 variables, the public keys are going to be huge, like 3 million bits, because there's for how many possible terms are there in each polynomial, given that there's 150 variables, any pair of them can be a term. You have to, if it's 5 bits for each coefficient, you have to multiply that by 5. So with 50 equations, that's kind of annoying. But at any rate, these things have small signatures, so that's what makes this thing nice, but the public keys are kind of annoying. So suppose you want to sign a 256-bit message digest of some message. What you do is you encode the hash of it in base 31, so you have 50 digits. You'll have this 256-bit thing that you break into 5-bit pieces, and you set each one of the equations to one of these pieces of the hash. And if you know the magic trapdoor, which I haven't explained yet, you'll be able to solve the equation, but the public key doesn't let you know this trapdoor. So, okay. So this is the actual multivariate signature scheme, which will hopefully be something that we could choose from eventually. It's called Unbalanced Oil and Vinegar. So what you do is Alice creates a set of polynomial equations that Alice can solve, but so can anybody else if they saw that. And then you create a related set of equations that only Alice can solve. So how do you do this? Well, Alice starts with what we'll call constrained quadratics. They're not really quadratics. And what it is you generate 50 quadratic polynomials with 150 variables, with the constraint that 50 of the variables we're going to call oil for no good reason, and the other 100 are called vinegar ones. Now, the constraint is that you can never multiply oil variables by each other, but you can multiply oil variables by vinegar variables, and you can multiply vinegar by each other. These guys clearly never cooked or anything, because I don't know why vinegars can mix with each other, oils can't mix with each other, but whatever. It's a very clever scheme, but I wouldn't trust them in a kitchen. So oil times oil is illegal. Oil times vinegar is okay, and vinegar times vinegar is okay. So yeah, the terms that have an oil times an oil all have coefficients 0. So what can you do that? What you do, as I said, that's the constraint. So what Alice can do is she can just choose random numbers for the vinegar variables, and she'll be left with linear equations in the oil variables, and she can solve those because they're now linear. So now what she needs to do is disguise which of these are oil and which are vinegar. And the way that she does that is she has 50 oil variables, 100 vinegar variables, and 50 randomly generated constrained quadratics. And so she's going to randomly select 150 linear obfuscation equations that are going to convert the oils and vinegars into x's instead, some other variable, that once she knows how to map them. Once she does that, it looks like quadratic equations, and nobody else will be able to know, the secret that allows them to solve this. So she replaces the O's and the I's, those variables, with these X's, and now it just looks like quadratic equations, and they're infeasible to solve. So anyway, this I don't want to talk about. Okay, so I think we should go to code-based. That gives you a taste of what the multivariate are. And the nice thing about multivariate ones is the signatures are extremely small, but public keys are annoyingly big. Okay, so the next family that I'll talk about is code-based, where code means like error-correcting codes. Okay, so for an error-correcting code, there's two functions. One will take a k-bit string and add redundancy to it. So it becomes what's called a bigger string, which is known as a code word, which is k plus enough extra bits that if there are errors, you can recover k. That's what an error-correcting code is. So you need to be able to convert a k-bit string into a code word, and then you have to take a mangled code word, a code word that has introduced some errors, and be able to figure out where the errors are. And those are the two functions that you need. So for an error-correcting code, you take a k-bit string and convert it to a code word, which is a bigger string, which and then you can mangle it by adding errors to it. And, the second function can figure out where the errors are in order to then be able to recover the original string. So, this particular scheme is based on an error-correcting code known as MDPC, which stands for Moderate Density Parity Check. So to create her public key, Alice comes up with the two functions, something that takes a string and converts it into a code word, and another function that takes a code word with errors and figures out where the errors are. So to send Alice a secret, Bob, who knows how to create a code word, takes any string, creates a code word, and then decides where to put errors in there. You can think of it as an error vector again, and mangles the code word by introducing these errors. And then Alice, because only she knows how to do the inverse function, can figure out where the errors are. So the secret is kind of a hash of the errors. So this is kind of similar in spirit to the lattice thing I talked about before. So yeah, Bob creates a code word, exclusive ORs Y with the error vector to create what I call a mangled code word, Y prime. And only Alice, using the private key, which I haven't explained, can feasibly compute the error vector. So Bob is going to choose where to put the errors. So that's the error vector here is where the red lines are. Now, when you have, how do you get a function from a k-bit message to an n-bit code word? It's done by multiplying the k-bit string by a k by n matrix known as the generator matrix. So you have a k-bit string multiplied by a k by n matrix will give you an n-bit string. So the way she's going to define her error correcting code is with the generator matrix, which will generate all possible code words. Right. And arithmetic is mod 2 in this scheme. So addition and exclusive OR and subtraction are all the same thing. You know, if you have two ones, the result will be a 0 and a 1 and, you know, whatever. So now there's one extra concept, which is systematic form. If you take a k-bit string and the code word results in having the same k-bit string in the beginning and then extra check bits, that's known as systematic form. It doesn't have to be that way. It could be that the n-bit thing looks sort of, you know, you can't really obviously see what the string is, but this is, we're going to be using systematic form. So to do a systematic form, part of the generator matrix has to be the identity matrix. And the identity matrix is one where everything on the diagonal is ones and everything else is 0. So with the identity matrix, if you take a k-bit string, multiply it by the identity matrix, you get the exact same k-bit string again. So hopefully you're sort of following me here, but I'm going quickly, I know. So this is what the generator matrix looks like for systematic form. There'll be an identity matrix on the left so that when you're multiplying the string, the first k bits are going to be the same k bits. And then the right part of it will be kind of the redundancy part, and that will give you the kind of check bits. So to send a secret to Alice, Bob chooses a k-bit string, multiplies x by the generator matrix, that is Alice's public key. He gets an n-bit code word, and which looks like the original string x concatenated with these check bits. And Bob randomly chooses an error vector with up to t ones. You know, the error correcting code can only correct for a certain number of errors, in this case t, and he has to make sure that the error vector has at most t ones. And he XORs E with the code word to get a mangled code word. So yeah, you take this code word in systematic form, you exclusive OR it with the error vector, and that's what you send to Alice, is the mangled code word. And she, with her private key, which I haven't explained how she does this, can figure out where the error bits are. So if you have a mangled code word and you want to do kind of the inverse thing and find out where the errors are, there's a related matrix related to the generator matrix, and it's known as the parity check matrix. If you take a code word and multiply it by the parity check matrix, the answer will be 0. If there are no errors, right. But if you multiply a mangled code word by the parity check matrix, you'll get this value, which is called the syndrome. Okay. So how is the parity check matrix related to the generator matrix? The generator matrix times the parity check matrix will be 0. Now, just like with the lattice things, where there's lots and lots of basis vectors that will generate the same lattice, here, again, lots and lots of generator matrices will come up with the same code words. So basically, you can take the generator matrix and multiply it kind of by any invertible matrix, and you'll get another equivalent generator matrix. And likewise, the same thing with the parity check matrix. So don't worry about that for the moment. So G, which is the generator matrix, times H is 0. An unmangled code word times the parity check matrix is 0. And there's many G's and H's that will work for the same code. Okay. So how do you use the parity check matrix to find errors? This will only work if the parity check matrix is sparse, meaning at most 1% of the entries are ones. So what you do is you multiply the mangled code word by H to get an n minus k bit vector known as the syndrome. And if there were no errors, the syndrome would be 0. But okay. But if there were errors, the syndrome is the sum of a set of rows in the parity check matrix. So if the parity check matrix, I see, I'm going backwards. As long as there aren't too many ones in the parity check matrix, you can take the syndrome and you look for the row that has the most ones in common with the syndrome. And so if it's the third row, you say, I think if the third bit in the thing that I got was an error, then I'm going to have to add that row into the syndrome. So if there was only like 1 bit error, then it would equal, the syndrome would equal the third bit in this thing. And so, the trick is to try to find a set of rows in the parity check matrix that add up to what the syndrome is. So you kind of do, trial and error. You guess that it might be the third bit, and then exclusive OR that row with the syndrome, and hopefully you get rid of some bits. But it could be that there'll be extra bits that get turned on because you had to do that thing. So you do, trial and error, and you might actually never terminate, or you might have to go back, and a row that you had tried before, you'll have to then get rid of. Yeah.
6 minutes, we can move on.
Okay. So, that's basic. Well, okay. So I think this is kind of the last thing in here anyway. But the trick of doing this, Alice starts by generating a parity check matrix, which is very sparse. And break it into 2 pieces like this. If she multiplies both sides, both matrices by B inverse, then she will wind up with something on the top which is not sparse anymore. And if it isn't sparse, you can't solve anything with this. And so her public key is going to be the non-sparse thing. So it's A times B inverse, which isn't sparse. So it's sort of, you can use it to generate code words, but you can't solve these things. Okay, that's probably, and this is probably too much too. Yep. There's different kinds of error correcting codes. What we described is moderate density parity check ones. But they're kind of annoying because sometimes Alice's procedure will not terminate, or it might find a different code word, which was close enough. There are other types of error correcting codes known as GAPA codes that are better behaved. They're harder to understand, but they're better behaved. But they're not as optimal because you can't use circulant matrices with them. So that's these. So the state of the NIST competition, they've already standardized, well, there's stateful and stateless hash-based signatures. Oh, okay, we don't have to go into that. That's so incredibly nice. Yeah, so, right, okay, we won't talk about that. So I'm going to just kind of review things. So again, not true, things on this slide, not true. That quantum breaks all of cryptography. Again, it only breaks our currently deployed public key algorithms. Any program would run zillions of times faster on a quantum computer. No, no, no. These are very, very different algorithms. Almost any computer program that you can imagine would not run at all on a quantum computer. So, yeah. And quantum computers are the next big thing. There'll be a huge commercial market for them, and probably not, but, who knows. So, okay, so I guess that's it. So, thank you. So, right, hopefully there'll be some questions. Any questions? Yes?
So you said earlier that because we only get a probabilistic result coming out of these operations, that what we do is we process the qubits in such a way so that the correct answer turns out with a very high probability almost being equal to 1. Does that constrain the kind of the sort of set of problems that can be computed in that way, or is it an inconsequential alteration?
Well, it means you have to come up with an incredibly clever algorithm that, without doing any sort of reads of intermediate states, you can actually raise the probability of the thing. But Shor's algorithm is not really so probabilistic. It's sort of, it will work,
Well,
right?
yeah, I mean, it'll produce a point, with overwhelming possibility, produce a point somewhere near a spike. And, right, so it's you can make the probability be fairly high. Oftentimes the way it's done, in Grover's in particular, sometimes you actually might not want to run it long enough to have the probability be near 1. You might be able to, in 3/4 of the time, get something that'll work 90% of the time. And it's actually faster to do that, and if it doesn't work out, you just run it again. And on average, that will be the winning strategy. So it's
Right, Grover's is more kind of probabilistic like that. Shor's algorithm isn't so much that way. But yeah, it's these things are astonishing that anybody was able to figure out how to do these algorithms. And again, there's so many people that I know that keep thinking of a quantum computer as a faster classical computer, and it's not. Yes?
Maybe I'm understanding things incorrectly, but these algorithms are considered post-quantum because their security does not depend on integer factorization, right? And thus they aren't susceptible to Shor's algorithm. Is there any guarantee or reason to believe why these problems are not susceptible to any other quantum algorithms, maybe ones that haven't been discovered?
Right, excellent question. It could be that, someone other than Shor comes up with some algorithm that would solve multivariate equations or something like that. But it seems very unlikely because kind of the type of problems these are just, don't seem as amenable.
right. I mean, there is no guarantee, but there is reason to believe. And the reason to believe is that I believe that all of these things are based on problems that have been shown to be NP complete, as opposed to factorization, which is known to be easier than that. And so there's good reason to believe that quantum computers will not be able to meaningfully accelerate the solution to these. it's always possible. There's lots of clever people out there trying to do these things.
Right, and furthermore, any of these things might have attacks on a classical computer, and somebody might figure out, just like with the isogeny thing, where somebody showed that they completely break it. So there's no guarantees of these things. That's why people are a little bit nervous about really new algorithms. There's certainly, the longer they're around, the more the cryptographic community has kind of stared at these things, come up with proofs and whatever, the more reassured you can be. But yeah, who knows? These things could get broken.
These problems are, turn out to be NP complete, and we manage to prove that P is not equals to NP.
Is not equal or is equal?
Is not equal to NP,
yep.
which is likely, right?
Right.
That means we're basically guaranteed that it's very hard to solve in a deterministic Turing machine, right? Very hard to solve with a deterministic Turing machine. Does it guarantee that it's also very hard to solve?
On a quantum computer?
On a quantum computer? Is a quantum computer a deterministic Turing machine?
Yeah, it's, is P equal to NP is the non-deterministic. There's also QP, those that can be solved on a quantum computer, and that's also an open problem. Is QP equal to
Right.
P?
Right.
Yeah.
It's widely believed, but hasn't been proven, that QP is bigger than P, but smaller than NP. And
I see.
right, and so
it's not a guarantee. So,
but yeah, there are no guarantees in this space, unfortunately. It turns out it's very hard to prove that problems are hard.
Right, and so like people like to have security proofs, but my cynical, don't quote me to cryptographers, but my cynical view of a security proof is that you take properties you assume properties of the scheme that there's no reason to believe that they have, and assuming those properties, you prove that it has properties that probably are not relevant anyway, but there's a proof there. I don't know. Yeah, it's often you have proofs, but it still is insecure for various other reasons. The proofs can make you feel better about it, but even having proofs doesn't necessarily mean that the thing won't.
Right.
And then there's whether the implementations have bugs too.
Right, and there's also that even if the math problem that we think is hard actually is hard, in the course of modifying it to turn it into a public key crypto system, they always make some, rejiggering of things, and that might make it much less secure than we thought it was.
Yeah, so for instance, if you have a random matrix, it might be more secure than if you use one of these circulant matrices that makes it like so much more efficient. Yes?
Given all of the limitations that you guys helped us understand today, I'm just curious, what applications or uses of quantum computing do you think might actually come to fruition?
Yeah, there's a lot of hype about this, and I'm a lot less enthusiastic about there being a large market for it. I doubt whether people will ever own them. There might be like a quantum computer in a public cloud that you could rent time on. Maybe a few drug companies or something will have enough money that they'll do it, but I doubt if there will be, it will ever be worth it. There will ever be a commercial application of it that it will be worth it to have a lot of them, but who knows? People are trying to work on finding applications for it.
Right. Yeah. I mean, it isn't where I'd be investing my money, but it's possible that it'll have applications to lots of weird things that we don't really anticipate.
Sorry, just to join in with that, aren't a lot of people excited about the ability of these computers to simulate physical systems that do exhibit quantum behaviors and that allow us to sort of peer into potentially make advancements in material sciences, drugs, and I mean, it's blue sky thinking again. Who knows what we'll discover from that? But concretely, that's a good and important use case, isn't it?
Yeah, that's sort of the most plausible thing. People come up with, so this is like coming up with drugs because you can simulate quantum systems or something, and it seems like a quantum computer ought to be good for that. There's optimization problems. Now, that I am not excited about, because in the real world, nobody needs to know the optimal solution to anything. They just need to know a pretty good solution. And there's absolutely no evidence that the kinds of things that these quantum computers that can do optimization, there's no evidence that those solutions are any better than you can do on a classical computer with good heuristics. And yeah, and then people talk about big data. They say, oh, wow, look how much state you can represent in a single qubit. It's sort of like but not in any useful way, because you can't read it. And furthermore, if it's just sitting around for more than a few seconds, it's going to lose its state. So I don't think big data is going to be one. But, it's something that is one of the areas of research, is coming up with problems. The other thing is, it takes so much research money to do research in this, and it's important to do research. So you have to kind of hype it and be very enthusiastic about, oh yes, give us millions of dollars because your return on investment is going to be astonishingly great.
Yeah, and I would compare it to sort of investment in the, superconducting super collider, where they're, discovering all these high energy, things and kind of thing. There might be amazing things to be discovered there, but there might also be nothing of any practical use. Nobody knows.
Okay. Questions online? Yes. Oh, okay.
Oh, yes. So do you think quantum computing can help reduce processing and computing for cryptography and blockchain, thereby reducing carbon footprint?
Do you want to take that one? I mean, certainly proof of work. So, it takes 2 nuclear power plants of energy to keep Bitcoin operating, and it's a very low volume kind of thing. So, you might think, well, what if we come up with a more efficient hash that you can compute more quickly? No, that's not going to help. Whatever it is, the whole idea is that it's only secure because it requires all of that computation. Now, proof of stake isn't, I mean, if it works, I'm still a little skeptical of it, is not inefficient. So that is not something that we desperately need some way of making it way more efficient. So, anything more to say? Okay.
Second question, what are the future challenges, complexity of problems which need quantum computing? What kind of programming software tools needed? Any qubits, Python, can say Quithons?
Right, and that's, we talked about that earlier. We don't really know what the problems are. There are people that have been investing in generating programming languages for quantum computers. That strikes me as a little bit premature, because the first ones that people are going to be carefully coding in assembly language to get the right thing. But yes, if they ever became mainstream, that would certainly be something that you'd work on, and you would program it quite differently, and so developing good programming languages would be a good thing.
Yeah, so in terms of programming languages, there's lots of students that, oh, quantum is bright and shiny, I want to study it. So the application of programming languages is so that you can give students problems and they can play around with this. But in terms of practically solving problems in the real world, I don't see that it's particularly useful to be doing that. And a cynical thing is, I was a math major. I do not understand why the world needs so many programming languages, even just on classical ones. So I'm just not enthusiastic about programming languages, but the reason people are trying to come up with it for quantum computers is just so that students can start learning this.
Well, and because quantum computers would be one of the cases where it would quite very much justify a new programming language because you have to program
yes.
things so very differently there.
Right.
The last question I think up there is the most interesting one, which is, somebody is talking about these optically trapped, yet another way of building qubits. There have been various competing approaches to qubits from the spin of microscopic superconductors to atoms spinning around inside vacuum magnetic bottles inside bubbles and things, and they've been leapfrogging one another as they make very advances. And this is anticipating another advance that brings things up to 2,000 qubits. It's still, to attack RSA that anybody's using, people were estimating 20 million qubits. So an advance from 50 or 100 qubits up to 2,000 qubits would be an important advance, but we'd still be a long way from things that are useful. So yes, I expect steps like that will come along, and they're important, but they're only steps.
Any more questions? Anyone?
Well, we'll be hanging around so people can ask us questions. Right.
Yeah. But somebody else is on.
Okay. Yeah, and we may have talked through the coffee break.
Yeah.
Yeah.
Don't go. There's we'll need your signature. We need to sign an autograph. Okay. Before I go a little bit further, in this presentation, talk about error correcting code. And this reminds me of a famous computer scientist called Hemming code. And he made a statement which is quite controversial. He said, God errors. Hemming himself corrects them. Okay. Anyway, why don't you select who asked the most difficult questions?
Right.
You don't remember?
Yeah, I'm sorry, I don't remember. Yeah,
Yeah, I don't.
yeah, it's, Sophie's choice. Yeah.
Now, this is called decentralized censorship, politically correct. I'll select them.
Right, it has to be somebody that actually would read it, because it is kind of deep and mathy. It's yeah. And even better would be a professor that might actually be using it in a class, or a student who's going to become professor who would be sort of best for us.
Now, let me make a disclaimer first. There are people in here ask the questions. They are somehow related to Polarization labs, okay?
So we can't choose those.
No, if it's deserved, it's okay. And in my opinion, the person asked the most difficult question is our distinguished engineer, Alice Lim. Okay, so
Okay, I'll sign it.
yes, sign, okay.
Yeah.
All right, thank you.
I'll give it to you now, but we're not going to sign it right now.